Hey folks, it's Mr. Ray here with our next lesson in grade 11 University Math. We're working in the unit called Functions and Transformations. Our second lesson is called Function Notation and Mapping. So in the first lesson we learned what's the difference between a relation and a function. And we also learned what domain and range were for a relation or a function. And how to tell by using things like the vertical line test, looking at a graph to see if a relation is a function. So today we're going to keep going, talking about functions. So our first definition here, it's actually a two-parter for function. The first part of the definition is what we learned last lesson. So a function is a relation in which each value of the independent variable, which is like your x, corresponds to exactly one value of the dependent variable, which is normally y. We're now going to extend that a bit, talking about function, and we're going to be talking about this part of what a function is. So a function is a rule that takes an input, does something to it, and gives a unique corresponding output. Okay, so that sounds a little complicated. We're going to talk quite a bit about that today. And then the second part of what we're going to be looking at is something called a mapping diagram. And it's also related, it's a little bit like ordered pairs or a table of values, but it's a different way of showing it. So we'll talk about that after we talk about function notation. So there's a lot of information here. Rest of this page is all about function notation. So there's a lot in here. I'll kind of chip away at what it is, and hopefully by the end you've got a good feeling for it. Then we'll do some examples where you apply what we've hopefully learned here. Okay, so function, we were just basically repeating this. A function is a rule that takes something as input, does something to it, and gives a unique output for that input. Okay. There's a special notation, it just basically means a way of writing it, called function notation. Not sure why those quotes are down there. Function notation, and that's obviously important. That's the name of the lesson. So function notation, it's used to represent this situation. Now I'll give you kind of how does this relate to what we've done in the past. Well, in grade 9 and 10, we might have had a linear relation or quadratic relation. For example, we'd have an equation for a linear relation like y equals 2x plus 1. Okay, so basically, you pick a value of x. It can be anything. You plug it in here, multiply it by 2, add 1, and you get your y value. Okay, so we're updating this. The way we're talking about this, we're still going to be using x as our input, but the y here, even though we're still going to be calculating the y coordinate if we graph it, in terms of the actual equation, we're going to start using function notation. So function notation actually gives a name to the function. Okay, and normally by default the function is going to be called f. We could actually name it anything we want other than the letters of our variables. The reason why we pick f is because it's the first letter of function. Okay, so we're going to, instead of calling our output y, we're actually going to be calling it f, and then in brackets I put x, and then the right side is exactly the same. Okay, so what's being updated is we're no longer making our equation with the y in it, where the left side is, now the way you would actually say this is f of x. Okay, it's not f bracket x bracket, it's f of x. You have to get used to saying it that way because everybody in the world says it that way. So f of x equals 2x plus 1. So what does this mean? Okay, so f of x is basically the y value you're calculating, but we're calling it this for a few reasons. One is starting in grade 11, we might have multiple functions that we're talking about at the same time. I might have a linear function, I might have quadratic, I might have something else. If I had multiple equations that all started with y equals 2x plus 1, y equals negative 3x squared, it's getting confusing because you got the three equations that make it look like y is going to be the same thing for all three. So because we have the potential to have multiple functions, we're going to give each function that we're using a unique name. So if I had a second function, maybe it's quadratic, I'm going to call that, give that function name, going to call it g. So in this case, it might be g of x equals 3x squared minus 8. Okay, so here I've got actually two functions, a function f and a function g. Now, this function f, what's inside the bracket is what we're basically using as input to this function. So this is defining the function. It says the input's called x, and what we do to the input x is we multiply it by 2 and we add 1. With the second function g, we're also using x as our input variable. And what we do to that input, you can see over here, we take that input, we square it, we multiply it by 3, and we subtract 8 to get our output. Okay, so that's basically how we're updating our relations from grade 9 and 10. We're now calling them functions, and we're giving each function its own name, and we're showing what input are we using and what do we do to that input to create the output. Okay, so let's go through some of these points here. Maybe it make a bit more sense after I've explained that. Okay, so I'll read this part again. There is a special notation called function notation that is used to represent this situation. If the name of the function is f and the input name is x, then the unique corresponding output is called f of x. Okay, so what I didn't talk about, I don't think I did, this f of x and this g of x, that is the output. Okay, f of x is the output of this function, g of x is the output of this function. The input, we're using the same letter x, and we have different names for the functions. This function is called f, this function is called g. Okay, so let's go through this. And I already mentioned this, the notation f bracket x bracket is read aloud as f of x. What exactly is f of x? It's the output from the function f when the input is x. So there's the input, there's the name of the function we're using, and f of x is the output of the function. So if I change things up a bit, I've changed the f to a g and the x to a t. So what does that mean? What does g of t mean? It's the output from the function g when the input is t. So the thing in the brackets is the input, and the letter to the left of the brackets, that's the name of the function. And this is really important. This is something I see mixed up quite a bit. F and f of x are not the same thing. F is the name of the function, which we could call the rule. We're going to talk a bit more about that. And f of x is the output when this rule is applied to the input x. Okay, so don't think that those two are the same thing. They're obviously related, but they're not the same. Now, I think this analogy here is a pretty good one. And I'll just kind of read what it says here and then talk about it. It's often helpful to think of a function as a box or a machine. You drop an input in the top and something happens to the input inside of the box / machine, and the output drops out the bottom. The box is labeled with the name of the function. Okay, so here's our analogy. So we have this magic box called f. F is a function, and this function takes some input, which we're calling x. It does something to it, and it sends the output out as f of x. So x comes into the function f, and f of x comes out of the function, which tells you which function it used, f, and it also tells you which which input it used. Okay. So I've just said this: if f of x is if x is dropped in the top of the box labeled f, f of x comes out the bottom. If we change this up a bit, if I had a function called t, the function's g, if I had my input t dropped into the box labeled g, which is the function, then that function output would be called g of t. Okay, so hopefully that makes a little bit of sense. So we're basically, after today, we won't see hardly any equations ever that are like y equals 2x plus 1 or y equals anything. We're going to be replacing this with the function notation, f of something, or whatever the function name is, g of something. Okay. All right. Before we start some examples, we'll just go through the description of what a mapping diagram is. So here is a mapping diagram down here. You notice I've got two ovals. Inside the ovals, I've got some numbers. And I'm labeling the oval on the left domain and the oval on the left range. So remember, domain is like all the possible values of your input, or your x values usually, and the range will be your output values for that that can be created from this function. Okay, and what you can see here is here's where the mapping comes in. You draw a line from the domain values towards the range values. Now, you just don't randomly pick it. We'll see some later on where we make our own mapping diagram. But this basically says, if I give the function the input of 1, it outputs 1. So so there's a point. If I was to graph this function, there would be 0.11. If I fed the function the input of 2, it outputs 4. So that's a 0.24 on the graph, etc. So I've got 5 different points on the graph, 5 different entries in the table of values. That's basically what this says. Okay. So we'll look at some examples of that after we've covered some more on function notation. Okay. Let's see what this says, if it adds anything new. In function notation, the symbol f of x represents the dependent variable, previously known as y. It indicates that the function f is expressed in terms of the independent variable x, because x is inside the bracket. And this is basically what I just said at the beginning. The equation y equals 3x squared minus 5 is now going to be written as f of x equals 3x minus 5. That's the function notation version of what we previously used. Okay, relations and functions given as ordered pairs can be represented using mapping diagrams, which we've just talked about here. This involves using directed arrows, and notice the arrows are always pointing from domain to range. There's only one arrow; it's always on the right side. Directed arrows from each value in an oval representing the domain to the corresponding value or values in an oval representing the range. In a mapping diagram, a relation is not a function when an element from the domain, the left oval, has 2 or more arrows leading to different elements of the range. So in this case, this would be a function because each value of the domain has one unique value, associated value in the range. If I had maybe had a second arrow that went from 1 to 4, well, that means for the x value of 1, I've got 2 possible y values, and we learned that in lesson 1 that if that happens, that's not a function. It fails the vertical line test, so it's not a function. Okay, so let's start in some work here, see if we really get this. So there's some quick questions here based on what we've just learned. What does the function notation of g of 7 represent? Okay, so remember, this whole g of something, that's the output. So I'm going to say this is the output of function, and we know the name of the function because that's the letter. The letter's g, that's the name of the function. So it's the output of function g, and the input we used was inside the brackets using input of 7. Okay. Suppose f of x equals x plus 2. What is f of 3? So this is the first time we've actually, we've defined the function using function notation. Now we're actually going to use function notation like this. So if f of x is x plus 2, what we're saying here is we're changing the input from x to 3. So I'm going to rewrite this with I'm changing the input x to 3. So everywhere I see an x, I also change it to 3 on the right side. So that's a 3 plus 2, and that's equal to 5. So f of 3 is equal to 5. So that's basically the y value for the x value of 3, if I was making points on the graph. So this is the output. The output is 5. The input was 3. Okay, this one's a little bit trickier. If f of x equals x plus 2, same as before, what is f of x plus 5? Well, this looks a little strange because I've still got an x in there and I'm adding 5 to it. So all you really have to think about here is, okay, I'm using function f, which is defined here, and I'm using x plus 5 as the input. So here I'm using x as the input. So if I change the input from x to x plus 5, just like up here when I changed the input from x to 3, everywhere I saw an x, I changed it to a 3. Now everywhere I see an x, I'm changing it to x plus 5. So I'll put it in brackets just to show that so I changed the x to x plus 5, and then I still have my plus 2, which is part of what the function does. It adds 2. And now I can just simplify this. So, I still am going to have an x in my output here, but I can combine the 5 and the 2. So the f of x plus 5 is equal to x plus 7. So if I was to describe what does this mean, it means the output is x plus 7 for the function f if I give x plus 5 as input. And I know that's sounds a little confusing, but basically think of this as the machine, okay? And the definition of this function f says that we're feeding this machine input of x, and what's happening here defines what the function does. It takes that input and it adds 2, okay? So all we're doing is saying, okay, we're going to change the input. We're still using the same function f, but now we're feeding it x plus 5. So we take the x plus 5 and we add 2 to it because that's what the function f does. So x plus 5 plus 2 is going to be simplified to x plus 7. Okay, so hoping that makes sense to you. Okay, the next part here. Suppose g of x equals 3x plus 2. Describe in words what the function does, what the function g does. So I talked a bit about that before. Basically, remember this, that's the input. This is the name of the function, g. So the function g takes x as input, and you can tell by what's going on here, what is this function g doing to the input. So the input is x, so you can just, mathematically see what's happening to x here. Well, x is being multiplied by 3, and then we add 2 to it. So that's what the function g does. It takes the input, multiplies it by 3, that's the 3x part, and then adds 2. So if you want to ever know what a function is doing to the input, you basically go through the BEDMAS here and see what's happening to the input, which in this case is x, and you can get basically a written description of what this box called G is actually doing. It's taking the input, multiplying it by 3, and adding 2. Okay, let's try this one here. Write function notation for the multiply by 5 rule. So basically what that means is multiply by 5 rule means whatever I have as input, I'm multiplying it by 5. Okay, use f as the name of the function and t as the name of for the input. Okay, so right away, if I know I'm writing function notation, there's the name of the function. What's the input? We're calling the input t. And what does this function f do? It tells here it multiplies by 5, which basically infers multiplies the input by 5. So the input is t. We're feeding it t. This is defining the function. So we're taking t, multiplying it by 5. So how do you write that mathematically? You could just say 5t. So it takes the input t, multiplies it by 5, and that's the output. Okay? So this is describing what the function does, and this is defining the function itself by knowing what the function does. So these two are like opposite. Okay. So we're going to practice using these in example 2 here, these predefined functions. They're all called function f, but obviously they're different for different questions. In all 3 cases, we also have x as the input. That's pretty much standard. Most of the functions you'll see in the rest of high school will be called f of x. That's not always going to happen. You might have, for example, if you had a function that's measuring the height of a golf ball based on the time, well, you could do a better job of calling that function f. If you're measuring the height, why not call the function h for height, and why not call the input t, because you're going to be feeding that function the time in seconds. So you try to make the name of the function meaningful, but if there's by default, if there's no real meaning to what the function is doing in terms of an application, it's usually f of x. And then if there's another function that you're going to talk about at the same time, you just kind of go through the alphabet. G of x, h of x. You wouldn't usually use I of x, but k of x, p of x, those are all common names for functions. Okay, so this is actually saying for each of these functions, determine f of -2, f of 5, f of 1/2. So what this is doing is saying in all 3 cases we're using the function f, but we're using different inputs. So f of -2, and we've kind of practiced this a little bit, but let's get some more practice again. So that's saying x is the input, but we're changing x. We're changing the input from x to -2. So everywhere I see an x, I'm going to change it to a -2. Now, it's always good practice when you're replacing the variable with the actual numerical values. It's good practice to put it in brackets, especially for this case where you have a -2. If I put 2 minus 2, it looks like we're subtracting, but we're actually multiplying. And then, of course, you have 2 times -2 minus 4. And now it's just a matter of applying bed mass. So we do this first. -4 minus 4, and that's equal to -8. So f of -2 is equal to -8. And then we do f of 5. So once you've done one, it's pretty easy to do more of them. You just change what's inside the bracket to what your new input is. 2 times 5 minus 4. That's 10 minus 4, which is equal to 6. And then finally, we've got f of 1/2. So that's going to be 2 times 1/2 minus 4. 2 times 1/2, half of 2 is 1, minus 4 is equal to -3. Okay, so this is a fairly typical thing you'll be doing. Once you've got a function, you want to find some specific values of the function based on the rule and the input, you would basically do it like this. So obviously that's a linear function in function notation. Here is a quadratic function in function notation. So in this case, we do the same thing. So we're replacing, again, we're replacing x, the input, with -2. Okay, now you can see in this function we've got x here twice, so we're going to be plopping in the -2 in brackets twice. So it's 3 bracket -2 squared minus -2 plus 3, sorry, plus 7. Okay, let's do this all in once. So -2 squared is 4. 4 times 3 is 12. Here we have a minus -2, so that's actually going to be a +2, and then the plus 7 already. Combine those all together, we have 14 plus 7 is 21. Okay. So the process is the same no matter what the function is. It's just replacing the input variable with the value that's in the brackets that you're using as input now. So f of 5 is 3 bracket 5 squared minus 5 plus 7. So 5 squared is 25. 25 times 3 is 75 minus 5 plus 7. So 75 minus 5 is 70, plus 7 is 77. Then we have f of 1/2. So again, we're just switching the input inside the brackets. 3 times 1/2 squared. Thinking ahead here, obviously. 3 times 1/2 squared minus 1/2 plus 7. Okay, so 1/2 squared is 1/4. 1/4 times 3 is 3/4. Okay, then we have a minus 1/2 here. I'm going to change that to quarters so I can easily add these together. So minus 1/2 is the same as minus 2/4. And then I have plus 7, which I also want to change to quarters. So 7 in quarters is 28/4, so plus 28/4. And now I can easily combine these three because obviously the denominators have to be the same. So 3 minus 2 is 1. 1 plus 28 is 29/4. And I could change that to a decimal, but I'll just leave it as an improper fraction. That's fine. Okay, here we have another function, and we're going to be, this is kind of a strange looking function. We've never worked with one of these previous grades, but you can see it's got a 2x on the top, and then you're dividing by x squared minus 3. This actually is not linear, and it's not quadratic. It's sort of a mixture. We actually call this a rational function, which we'll talk a little bit about in the next unit. So it doesn't really matter what it's called, we still treat it the same. So that's our definition of f. The function f, what it does, it takes the input, multiplies it by 2, and then divides by the input squared minus 3. So let's change the input from x to what they're asking us, -2. Okay, so on the top I've got 2 times -2. On the bottom I've got -2 squared minus 3. Okay, so on the top I've got -4. And on the bottom, -2. This is why it's important to put your brackets around this, because you're squaring -2. It's not subtract 2 squared. It's -2 times -2, which is +4. +4 plus minus 3 is 1. So I guess I can do that. And then, so the answer overall is -4. And then if we change it to input to 5, I've got 2 times 5 over 5 squared minus 3. 2 times 5 on the numerator, that's 10. On the bottom, I've got 25 minus 3, which is 22. And I can reduce this to 5/11. Leave it as a fraction because the decimal goes on forever. All right, and then the last one, f of 1/2. This one's going to be a little trickier. So on the top, we've got 2 times 1/2. On the bottom, we have 1/2 squared minus 3. Okay, 2 times 1/2, that's nice and easy, that's 1. And here it gets tricky. So 1/2 squared, like we had up here, that's 1/4. And then minus 3. But again, just like I did before, let's change the 3 to something over 4. So that would be 12/4. So that on the bottom, that changes to negative 11/4. So if you remember your fraction math, if I'm dividing by a fraction, it's the same as multiplying by the reciprocal of this. So it turns into 1 times negative 4/11. So the whole thing is negative 4/11. Okay, so that's how you actually use function notation to evaluate certain input values. And this is something that you'll be doing lots and lots of. So make sure you understand that. Okay, we're going to do an example of mapping diagrams now. Make sure you understand what's going on there. So it says create a mapping diagram for each of the following sets of ordered pairs. State if the relation is a function. Okay, so if you remember the original picture on the first page or second page, you've got your 2 ovals. They don't have to be perfect. Make sure they're closed though. And I'll put D here for domain, R here for range. And remember, inside the domain oval, I put all the values of x that exist for this relation. We don't know if it's a function yet. So I'm going to put them in, ascending order. So I've got 1, 2, 3, 4, 5, 6, 7. These ones are in nice order already. Okay, and then the range, you can see it kind of hops all over the place. I got -5, -1, -5, 0, 0, 5, 5, and 8. So if I sort those in order from lowest to highest, I'm going to have -5, -1, 0, 5, and 8. You can see I've got more values in the domain than I do in the range, and that is possible. You can have both ways. They could be more in the domain or more in the range, or they could be all the same number. Okay, so what this mapping diagram is, now that we've got all the possible, this is basically all your possible x values, all your possible y values. Now we use our arrows to define, if I had 1 as my input, what's my output going to be? Well, you can tell from that ordered pair there. So 1 and goes to -5. So I draw an arrow from 1 to -5. Next one is 2 and -1. Well, there's that mapping from 2 to -1. That defines this ordered pair here. 3, -5. So -5 I've already used once. So I'm just going to draw another arrow going to it. 4, 0. Straight across here. 5, 0. So again, same thing, goes to the same point. So both 4 and 5, the input 4 and 5, both map to the output or the y value of 0. 6 goes to 5. And 7 goes to 8, which are defined by those last two ordered pairs, or points, if you want to call them points. Now, state if the relation is a function. So remember, the definition of a function says that each of your input values, your x values, has a unique y value or a unique output. So you'll be able to compare this to the next one easier. But in this case, I only have one arrow going from each of the domain values, and that tells me there's only one arrow going from each of these input values, the x values. That means that this is a function. So function, since each element of the domain has only one mapped element of the range. Okay, so that should make sense. There's basically one arrow going from each domain element. Okay, so let's try the same thing with this second set of ordered pairs. So start off the same. Domain range. Okay, now I'm going to put now remember, you only put, if you have multiple values for domain or range, you only put the same value here once. So for example, you can see I've got 2, 1, 2, 2. I'm not going to put 2 there twice. I only put it there once. It's got to be, you can't have duplicates in either one of these. Just like we, up here we didn't have -5 written twice or 0 written twice. We just had it there once, and if we used it more than once, you could see that because you have 2 arrows coming to it. Okay, so if I look at the x values of this set of ordered pairs, and if I put them in order, I've got 2, 5, 8, 11, 14. And then when I look at my y values, my outputs, 1, 2, 3, 7, 5, 4, 6. So if I put them in order, it's 1, 2, sorry, that's not 11, that was 5. So 1, 2, 3, 7, 5, 4, 6. So that's basically 1 through 7. So I'll put them in order just so you can find them easier because you know where to look. Okay, now we do our mapping. So in this case, I've got an arrow going from 2 to 1. I've got an arrow going from 2 to 2. 5 to 3. 8 to 7, so that goes down here. 11 to 5. And try to make these as straight as possible. I realize that mine aren't completely straight, but you definitely don't want them wandering around. It's got to be straight so you can follow them easily. So that was 8, 7, 11, 5, 14, 4, and 14, 6. Okay, now when we ask the question, is this a function? Okay, what we're looking for, like what we had here, this was a function because we only had one arrow leaving each domain element. But here, you can see the 2 has 2 arrows coming off it. So I had the ordered pair 2, 1 and the ordered pair 2, 2. Okay, that's a violation of what a function is, because a function can only have one unique value for each element of the domain. This one doesn't. This has 2. Same thing with 14. 14 has 2 arrows going off it, which means that element of the domain does not have a unique mapping or a unique output. Okay, so this is not a function. Since 2, and we can use the numbers, the elements that were violating the rule, 2 and 14, have more than 1. Mapped elements. of the range. Okay? You don't have to say it. You don't have, when you answer a question like this, it doesn't have to be quite as technical sounding as this. You can just refer to the rule that a function, each element of the domain of a function has one unique output, or in this case, one unique mapped value in this case. So these two are violating that rule, therefore it's not a function. Okay, so we've covered two important things in this lesson. Defined what function notation is, which is basically we're using that for the rest of high school and beyond. And we've also talked about mapping diagrams, how this is a way to show how a relation or function is defined in some cases. Okay, got some homework questions here for you to try, and thank you for listening. This will be the second lesson, and we're going to continue on looking at functions in our next lesson. Have a great day.